In part 4 of this lecture, I will talk about organic molecules and how we represent their chemical structure. So carbon is one of those 6 important atoms that you need to know about, and carbon is incredibly important for biological molecules because carbon and hydrogen form molecules that we call organic compounds. Carbon is important in this process because carbon is a relatively neutral atom that can form 4 covalent bonds with other atoms. Carbon always forms these 4 covalent bonds with other atoms because it has 4 out of 8 electrons in its outer electron shell. Because carbon can form these 4 covalent bonds, carbon can form the backbone of complex chains of carbon and other atoms that form organic molecules. Organic molecules can be as simple as methane, which is 1 carbon attached to 4 hydrogens. Right? But they can also be complex chains or rings, such as this fatty acid shown at the top, this amino acid in the middle, or this carbohydrate, the sugar at the bottom. So organic molecules are primarily composed of chains of carbon, and most of the atoms bound to that carbon, besides carbon itself, are hydrogen. But functional groups, where carbon binds to other atoms, give organic molecules their unique chemical properties. There are a number of important functional groups that you'll see in organic molecule structures. So hydroxyl functional groups, or OH functional groups, and remember oxygen is a very electronegative atom, and so these are polar functional groups. They give polarity to molecules that include the functional group in them. We'll see methyl or organic functional groups, so that's where there's a carbon with 3 hydrogens on the end. Remember the carbon with hydrogens attached to it has an equal distribution of charge, and so this is a non-polar functional group. We have other functional groups such as the double-bonded oxygen carbonyl. We'll have a carboxyl where we have a carbon with a double-bonded oxygen and also a hydroxyl. And carboxyl groups are able to release this hydrogen and participate in acid-base chemistry. We'll also see amino functional groups. Remember that amine is a key word for nitrogen. And this is a often polar and charged functional group. Amino groups are able to accept hydrogens to form ammonia, and since those amino groups remove the hydrogen from a solution, they are considered basic. We also have phosphate functional groups. Phosphate is a very charged, readily ionized functional group. So we see this functional group providing a lot of charged ionic interactions between molecules. And finally, this sulfhydryl functional group is a polar group that includes sulfur. One of the important concepts we want you to learn in this lecture is how we draw organic molecules. So here we have 3 different examples of how we draw the same organic molecule. So remember, this is a molecule of adenosine, and most of the atoms in organic molecules are carbon and hydrogen. Carbon forms the backbone of the organic molecules, and so most of the bonds in an organic molecule are carbon with other carbons or carbon with hydrogen. We can draw a shorthand of an organic molecule by, instead of showing every single carbon atom using the carbon chemical symbol C, we know that most of the bonds in the atom or in the molecule are formed by carbon atoms. And so if we draw covalent bonds and the intersection of 2 covalent bonds, without writing another atom, then that intersection of two covalent bonds is a carbon. And so here we see the intersection of two covalent bonds. Okay? And that's a carbon atom that you can see here in the same structure of adenosine over here on the left. Right? So that's the carbon that's forming a bond with the hydroxyl group here, and then the other carbon, which is the intersection of these three bonds right here. Okay, so here you see this carbon is the intersection of the two bonds. That's the same carbon that's on the left structure over here. This carbon is also, you'll notice, attached to two hydrogens. It's because carbon always makes 4 covalent bonds. You can see one of those covalent bonds is made to this hydroxyl group here, and the other covalent bond is made to this carbon here. And then there are 2 additional covalent bonds made to hydrogens. So we know that carbon forms 4 covalent bonds no matter what. And so if there are missing covalent bonds on this shorthand structure, we know that's because there are hydrogens that are also bonded to that carbon that are making up whatever covalent bonds are missing in the structure. And so by omitting the chemical symbol, the atomic symbol for carbon, and just showing carbons as the intersection of covalent bonds, and omitting those hydrogens that are attached to the carbons, we take out a lot of the clutter in the structure, but we still know where the carbons are because they are the intersection of the covalent bonds. And we also know where the hydrogens are because we know that if there's not a covalent bond shown making up the 4 that carbon always forms, then that's a hydrogen present on the structure. We'll also show 3-dimensional representations of molecules. So this is the same molecule over here. This is adenosine, but showing its 3-dimensional geometry. We'll sometimes represent the 3-dimensional shape of molecules in these structural diagrams by using chemical bonds or using lines that represent covalent bonds that are like slight triangles. So these little triangle bonds down here are trying to represent some of the geometry of this ribose ring that's part of the adenosine molecule. So one of the things we want you to get lots of practice of doing in this unit is recognizing and understanding these organic molecule structures. Okay? So we're going to practice here. Remember, there are many atoms in the structure that are explicitly drawn. So here we have a nitrogen, right? And it's attached to 2 hydrogens. Here we have a carboxyl group. We can see one of the oxygens with its double bond and the hydroxyl here. And then we have another amine functional group down here. So that's a nitrogen and the hydrogens that are shown on it. Then we have the carbons in this molecule. Remember, carbons are all of the intersections of covalent bonds with no other atom explicitly shown. So here we see 2 covalent bonds, and the intersection of those 2 bonds right here, that is a carbon atom. Another carbon atom here, and here, and here, and here, and here. So there are 1, 2, 3, 4, 5, 6 carbon atoms where we don't see the atomic symbol, but we know that those carbon atoms are there because they're at the intersection of these shown covalent bonds. The other thing we know is that carbon always forms 4 covalent bonds. So if we look at this carbon here on the right, we see it's forming 1, 2, 3, 4 covalent bonds with the atoms surrounding it. So all the covalent bonds for this carbon are shown. This carbon here, on the other hand, we see 1 covalent bond to that previous carbon, 1 covalent bond to the next carbon, and then 1 covalent bond that's showing the geometry in this little triangle shape to the amine down here at the bottom. That's 3 covalent bonds. We know carbon always forms 4, and so there must be a missing covalent bond that represents 1 hydrogen attached to this carbon. On these next carbons, we see two covalent bonds coming from the carbon to the previous carbon to the next carbon. We know that carbons form 4, and so there must be two missing hydrogens bonded to each one of these carbon molecules. So that's where all the atoms are in this chemical structure. Let's go back through that slowly by taking into account, by writing the chemical formula for this particular compound that's made of carbons, hydrogens, nitrogens, and oxygens. Now all the oxygens and nitrogens are explicitly written in this diagram. So you can see 1, 2 oxygens here, so this is an O2, and then 1, 2 nitrogens here, so there's 2 N's. The carbons, though, we are going to have to count because they are the intersections of those covalent bonds. We just did count them, but I'm going to go through them again. So we have 1, 2, 3, 4, 5, 6 carbons that are the intersection of covalent bonds. So there's 6 carbons in this structure. And then we can count the hydrogens. Some of these hydrogens that are attached to other atoms, so here, here, and here are all explicitly shown. So there are 2 hydrogens plus 2 hydrogens plus 1 hydrogen. That's 5 hydrogens that are shown. Okay. But then we have the hydrogens that are hidden that are attached to the carbons. So we know there are no hydrogens attached to this carbon because all its bonds are shown. There's 1 hydrogen attached to this carbon because we only see 3 bonds. And then there are 2 attached to this one, 2 attached to this one, 2 attached to this one, and 2 attached to this one. So if we take the 5 hydrogens that are shown plus 2 plus 2 plus 2 plus 2 plus 1, so that is 9 hydrogens that are not shown in this diagram that are just attached to those carbons. So the total number of hydrogens is 5 plus those 9 that are hidden. So that's 14 hydrogens in this structure of lysine. So lysine is one of the amino acids. So it's important to remember that organic molecules have 3-dimensional shapes. That's because the orbitals are actually in three-dimensional space surrounding the nucleus. That means that the same mixture of different atoms can form many different shapes of similar compounds. We can make enantiomers, which are mirror images of the same chemical compound. They have identical chemical properties, but distinct shapes. And enantiomers are a little like gloves. So if you think about your gloves, that you have a left and a right hand glove, and it's difficult to fit your right hand in the left glove, because even though you have the same combination of 4 fingers and a thumb on those hands, they are mirror images of each other, and they don't fit in the same pockets. Another important thing to note, especially when you practice drawing organic structures, is that the bond length between all of the different bonds in most organic structures is approximately the same. And so the space between different atoms in the structure is pretty similar, and so you should draw all of those bonds approximately the same length when you draw those organic structures.